Assalamu alaikum. I am Dr. Fatima Nur Jahan, lecturer, Department of Physiology, Shohid Sohrawardi Medical College, Dhaka. Today's topics are urine formation, glomerular filtration, determinants of glomerular filtration rate, and autoregulation of renal blood flow and GFR. Welcome to you all today's class. The filtration of large amount of fluid through the glomerular capillaries into Bowman's capsule. Now, what is glomerular filtration rate? It is the amount of glomerular filtrate formed by all the nephrons of both the kidneys in 1 minute or per unit time. It is about 125 ml per minute or 180 liter per day. Now, what is the composition of glomerular filtrate? It is similar to protein-free plasma, except half of the plasma calcium and most fatty acids are bound to plasma proteins and not filtered. It is devoid of cellular elements, including red blood cells. Most salts and organic molecules are similar to concentration in plasma. Now, what is filtration fraction? The fraction of the renal plasma flow that is filtered, it is filtration fraction. Filtration fraction is equal to glomerular filtration rate divided by renal plasma flow. So, it is about 20% of renal plasma flow. Renal fraction, fraction of the cardiac output that flows through the kidney. So, it is about 24% of cardiac output. Figure shows the basic processes that determine the composition of urine. Number 1 step is tubular glomerular filtration. Number 2 is tubular reabsorption. Number 3 is tubular secretion. And number 4 is urinary excretion. So, excretion is equal to filtration minus reabsorption plus secretion. Figure shows average values for total renal plasma flow, that is 625 ml per minute. Glomerular filtration rate is about 125 ml per minute and reabsorption is 124 ml per minute. So, urinary excretion is 1 ml per minute. So, finally, urine formation results from glomerular filtration, tubular reabsorption and tubular secretion, and urinary excretion rate determined by filtration rate minus reabsorption rate plus secretion rate. Now, what is the determinants of GFR? GFR is determined by the sum of the hydrostatic and colloid osmotic forces across the glomerular membrane, which gives the net filtration pressure and the glomerular filtration coefficient. So, GFR is equal to glomerular filtration coefficient into net filtration pressure. The GFR can therefore be expressed as Kf into Pg minus Pb minus pi g plus pi b. Here, Kf is equal to glomerular capillary filtration coefficient, which promotes filtration. Pg is equal to hydrostatic pressure inside the glomerular capillaries, which promotes filtration. Pb is equal to hydrostatic pressure in Bowman's capsule, which opposes filtration. Pi g is equal to colloid osmotic pressure of the glomerular capillary plasma protein, which opposes filtration. Pi b is equal to colloid osmotic pressure of the proteins in Bowman's capsule, which promotes filtration. So, summary of forces causing filtration by the glomerular capillaries. This is glomerular capillary hydrostatic pressure, which is 60 mm of mercury, which promotes filtration, glomerular corridor osmotic pressure 32 mm of mercury, which opposes filtration. Bowman's capsule hydrostatic pressure 18 mm of mercury, which oppose filtration. And finally, forces favoring filtration are glomerular hydrostatic pressure, which is above 60 mm of mercury, and Bowman's capsule corridor osmotic pressure, which is 0 mm of mercury. Forces opposing filtration are Bowman's capsule hydrostatic pressure, which is 18 mm of mercury, and glomerular capillary corridor osmotic pressure, which is about 32 mm of mercury, and net filtration pressure is equal to plus 10 mm of mercury. Now, what is filtration coefficient? The filtration coefficient is a measure of the product of the hydraulic conductivity and surface area of glomerular capillaries. Kf is equal to GFR divided by net filtration pressure. It is about 12.5 ml per minute per millimeter mercury and 4.2 ml per minute per millimeter of mercury per 100 gram of kidney. Increased glomerular capillary filtration coefficient, increased glomerular filtration rate, and decreased glomerular capillary filtration coefficient, decreased glomerular filtration rate. Now, what is physiologic control of glomerular filtration rate and renal blood flow? It is occurred by sympathetic nervous system activation, hormonal and autocoid control of renal circulation and GFR, and autoregulation of GFR and renal blood flow. Sympathetic nervous system activation. Strong sympathetic activation occurs during the defense reaction, brain ischemia, or severe hemorrhage, which can constrict the renal arteriole and decrease renal blood flow and GFR. Hormone or autocoid that control GFR. Most important is angiotensin II among hormone and autocoid. It helps to maintain GFR. Angiotensin II preferentially constricts efferent arterioles in most physiological conditions. Increased angiotensin II level raise glomerular hydrostatic pressure, which reducing renal blood flow. While reducing renal blood flow, angiotensin II formation occurs in circumstances associated with decreased arterial pressure or volume depletion or low sodium diet. Now, autoregulation of GFR and renal blood flow. It is feedback mechanism which is intrinsic to the kidneys. Normally keep the renal blood flow and GFR relatively constant despite marked changes in arterial blood pressure within a range of 75 to 160 mm of mercury. This relative constancy of GFR and renal blood flow is referred to as autoregulation. It has two components, tubular-glomerular feedback and autoregulation of GFR, and myogenic autoregulation of renal blood flow and GFR. Now, what is tubular-glomerular feedback and autoregulation of GFR? It helps to ensure a relatively constant delivery of sodium chloride to distal tubule. Helps to prevent fluctuation in renal excretion. It has two components, an afferent arteriolar feedback mechanism and an efferent arteriolar feedback mechanism. Tubular-glomerular feedback mechanism regulated by juxtaglomerular complex. Now, what is juxtaglomerular complex? The juxtaglomerular apparatus consists of macula densa cells, which is located in the initial portion of distal tubule, and juxtaglomerular cells which is located in afferent and efferent arterioles. So, Juxtaglomerular complex consists of macular cells in the initial portion of the distal tubule and juxtaglomerular cells in the walls of the afferent and efferent arterioles. And macula densa is a specialized group of epithelial cells in the distal tubule that comes in contact with afferent and efferent arterioles. Now, how macula densa feedback mechanism for autoregulation of glomerular hydrostatic pressure and GFR during decreased renal arterial pressure. When decreased renal arterial pressure decrease glomerular hydrostatic pressure, that decrease glomerular filtration rate. When glomerular filtration rate decrease, increase proximal sodium chloride reabsorption and decrease macular densa sodium chloride, which stimulates decrease afferent arterial resistance, causes increased glomerular hydrostatic pressure and increased GFR. Although when decreased macular densa sodium chloride concentration, increased renin secretion occur, which causes increased formation of angiotensin II. And we know that angiotensin II causes mainly increased efferent arterial resistance. And increased efferent arterial resistance causes increased glomerular hydrostatic pressure and result increased GFR. Opposite effect occur when increase arterial pressure. Now, myogenic autoregulation of renal blood flow and GFR. It is the ability of individual blood vessels to resist stretching during increased arterial pressure, a phenomenon referred to as the myogenic mechanism. It protecting the kidney from hypertension-induced injury. Now, myogenic mechanism. When increased arterial pressure, stretching of vascular wall, which causes entry of calcium from extracellular fluid into vascular smooth muscle cell, causes contraction of arterioles and increased vascular resistance, which prevent increased renal blood flow and GFR. Thank you all for patience listening.